Buenos días. ¿Estás tú cansada? Tenemos un gato ahí. Se llama Ivan. Hola, Ivan. Hola, gato pequeño. Él se duerme. Aprendí que linda quiere decir cute en español. ¿Es verdad? Okay, I'm going to start. Hope you guys had a good weekend. So I'm going to keep this to about 15 or 20 minutes, and then we'll go to the Zoom room really quickly and just check in. Hope everyone had a good weekend. So IB teaches us about electric fields, and then also, but we don't have to know a ton about electric fields. So we just had 1 week of electric field. Today, in this week, we're going to learn about magnetic fields. And again, this is another topic where we will just be touching on briefly because it's not a huge part of the IB exam if we even take the IB exam. Okay? So, today we are talking about the magnetic field. Okay? So just like there's an electric field, there is also a magnetic field. The magnetic field is denoted by B. B stands for magnetic field. So, just like you have the E field for electric field, you have the B field for magnetic field. Okay. So yeah, that's the B field. The units of magnetic field are called Tesla, which is abbreviated by T. Okay, so that is the unit of the Earth, or of magnetic field in general, just like the car, named after scientist Nikola Tesla. Okay, now to a typical value for magnetic fields. So, for example, the magnetic field of the Earth is like 10 to the minus 5 Tesla. So it's not very large. So having a 1 Tesla magnetic field is really quite strong. And in fact, the magnetic field that we can produce in a laboratory, so kind of like the strongest laboratory magnetic field, is like around 2 Tesla. Okay, so magnetic fields are, generally speaking, pretty small. Okay. So you might recall that when we were talking about the law for the electrical force, all right, the law for the electrical force is QE, all right, and for the electrical force, basically the rule was positive charge is pushed along the field and negative charge is pushed against the field. Okay? Now, just like there is a law for the how does the electrical force relate to the strength of the electric field, there's also a magnetic force law. And the magnetic force law is QVB sine of theta. Okay? So Q is the size of the charge in the field. Okay? B is the size of the field. V is the speed. Okay? And theta is the angle between the velocity, which is a vector, so it has a direction, and the magnetic field, which is also, the magnetic field is also a vector, so it has a direction. And so we have, maybe a magnetic field goes one direction, and then a velocity goes in a different direction. Okay. So a couple of things to notice about, so this is our main equation for today, this one right here. So what we want to notice about the magnetic field is, so let's make a couple of observations. Okay. One observation is that if you are at rest, okay, then the magnetic force is equal to 0. Why? Because then if you're at rest, then your speed is 0, so you have 0 times other stuff, which is still 0. Okay, so if you're at rest, there is no magnetic force. One of the things that's kind of counterintuitive about that is you might say, well, gee, if I have a refrigerator magnet and I hold it close to the refrigerator, the magnet is still, so why does it get pulled to the refrigerator? Why is there a magnetic force, even if the object is, as a whole, is still? And the thing is that even though your refrigerator magnet is still, the atoms inside the refrigerator magnet have electrons that are moving around, right? The electrons are orbiting the atoms, and it's those individual electrons within the material that are being pulled by magnetic fields, and that's what causes the attraction. So even though there's no macroscopic, when I say macroscopic, I mean sort of like human scale motion, okay, there is still a magnetic force because the individual electrons within the material are still moving, okay? Materials that are not magnetic, basically for every electron going one direction, you have an electron going the opposite direction, and so you change the direction of the velocity and you change the sign of the force, and so those forces cancel out, and there's no net magnetic force on the material, even though the individual electrons are being pulled. So that's kind of interesting. All right. So the other thing I want to point out is that if V is parallel to B, or V is anti-parallel to B. So when I say parallel, I mean velocity and magnetic field are both in the same direction. And when I say anti-parallel, I mean velocity and magnetic field are in opposite directions. So V being parallel to B means that the angle between V and B is 0 degrees. Okay? If V is anti-parallel, so parallel is 0 degrees. If I go anti-parallel, that's 180 degrees. Okay? So anti-parallel means theta equals 180 degrees. And you can try it in your calculator. The sine of 0 degrees is 0. The sine of 180 degrees is 0. So if your velocity is parallel or anti-parallel to the magnetic field, then there is no magnetic force. Okay. So this is kind of interesting because it actually explains the Northern Lights. Okay, why did the Northern Lights happen? Well, let's say this is the Earth, and the Earth's magnetic field actually goes into the North Pole. So here's the Earth is spinning about its axis. The magnetic field goes into the North Pole and out of the South Pole and kind of does loops like this. So this is what the Earth's magnetic field looks like. Kind of looks like this. These are the magnetic field lines, so analogous to electric field lines. And here's the Earth right here. Now, what if a particle from outer space comes in here? What if this is the direction of the velocity of the particle? Okay, if they come in from that direction, so here's the equator of the Earth, right? So if they come in towards the equator, you can see that the velocity and the magnetic field are like at 90-degree angles. So that's not 0 degrees or 180 degrees. So this particle is going to get deflected by the Earth's magnetic field. Okay? However, what if a particle comes in from the North Pole and it's coming down towards the, what if that's the velocity? Here, then we have the velocity and the magnetic field are parallel to each other, and so there's no magnetic force. So particles that come in from the North Pole direction, from a polar direction, are able to pass through the Earth's magnetic field and hit the Earth's atmosphere, which causes the Northern Lights. So the reason that the Northern Lights happen in the North Pole and they can also happen in the South Pole, is because of the magnetic force law combined with the way that the Earth's magnetic field is shaped. Okay? Now, if you're able to view the northern lights from a more southern latitude, that's because, it could be because the particles have a particularly high velocity so that they're able to penetrate the Earth's magnetic field, or the Earth's magnetic field actually does fluctuate over time. So there are various reasons. But yeah. All right, so let's do an example calculation. All right. And I think that'll more or less finish off our lesson, and we'll go to the Zoom room. Let's say that a particle has mass 4 kilograms, charge 2 coulombs, and travels in a direction, let's say 30 degrees north of west, with speed, let's say 170 meters per second in a 0.35 Tesla magnetic field. That points, let's say, 10 degrees north of east. Calculate the acceleration of the particle. Okay, so I'll give you a second to write that down. Okay, so what you want to do with magnetic field problems is see how we have multiple angles here? So you really need to draw a picture of the situation in order to understand what the angle in the magnetic force equation should be. Okay, so what I'm going to do is I'm going to draw out my compass rose. Okay, so we have north, south, west, east. Okay, and then my velocity is in a direction 30 degrees north of west. So what that means is I start with west, and then I go 30 degrees north of that, and that's the direction of the velocity. Okay? So here's my velocity in that direction. For the magnetic field is in a direction that is 10 degrees north of east. So I have eastward, and then I go 10 degrees above that to something like this. Okay? So that's 10 degrees. And here's my magnetic field. Now, theta is the angle between V and B. So the theta in the magnetic force law is that angle right there. All right? And we can see that all three of these angles have to add up to 180 degrees. So that means that this angle right here must be 140 degrees. All right, so that is the angle that we're going to use. So notice how it's not either of the angles that were given here. It's related to those angles, but it's not. So I highly recommend drawing it out so that you can tell what the angle is. So now we have the law for the magnetic force is QVB sine of theta. Q is 2 coulombs. The velocity is 170. The magnetic field is 0.35 Tesla. And the angle is 140 degrees. So now what I'll do is I will work that out. And I get that the force is 76.5 newtons. Then I'm assuming that this is the only force that is acting on the particle, so then I will do F net equals ma. And because that is the only force, my net force is 76.5 equals 4a. And so I can get that the acceleration is 19.1 meters per second squared. Okay, so that's my lesson for today, and I will see you in the Zoom room.